It's okay? Let me express my thanks to the organizers for the invitation. I was really happy to get the invitation, but then they said you have to give 2 talks. And I only had 1 ready. So I thought for the first talk would be introductory, but at a level that's already been covered by David and who spoke this morning? Jen, right. But the point of view, my pitch will be historical as well as from the ground up, right? So none of this fancy connection theory and differential algebra. And then how it relates to experiment. Science is a really human activity, right? And ideas sometimes come and go. And that's the case with this. If Luttinger hadn't encountered such vigorous resistance, our field would have been born 50 years earlier. Luttinger is one of these giants who I think is deeply unappreciated by our field. He really stands up there with Bardeen, Anderson, Landau, one of the founding giants. But he was always 30 years ahead of his time, and that's his misfortune. So this is the talk that's a tribute to Luttinger, and okay, let's see how it goes. So I'll talk first. I'll introduce you to his, if I think it out. I'll talk first about the well-known Luttinger couplets theory. Then I'll give you a rather physical feeling for what it was they discovered, although it took 2 other theorists to work that out. And you can see that from this, it's very evident why the transport equations that we all learned from Ashcroft and Mermin and Kittel and so on are incomplete. And I think that this is a very easy thing to see from this other point of view. Then I will go on to Berry curvature, and I will repeat the grounds already covered by Jen and David, hopefully from a more physical point of view. And then the Berry curvature actually has huge effects, right? Because sometimes theory says that, well, yes, this tiny correction at a percentage level. Berry curvature brings in effects that are completely outside the domain of semi-classical transport, but the effects are huge. And experiments had actually seen these effects many, many decades before we understood it. And I will list a few of them just to illustrate the point. In particular, the planar Hall effect. So this is something that I stuck in to set the stage for my second talk, which will be on the thermal Hall effect in Kitaev magnets. That was a talk I wanted to give, but I had to give this talk first. All right, so this planar Hall effect, I'll explain it, and it's all caused by Berry curvature. And then I'll close with the exciting discovery of the quantum anomalous Hall effect, which David has already introduced. And I'll give an experimentalist purview of why it was so challenging. Right? So they did, the group with Tsinghua and IOP really pulled off a real coup. Okay, so this sets the stage. So the first part is Luttinger theory. I won't repeat the derivation. David covered it very nicely. So as you all know, the semi-classical equations have these 2 simple forms, and this is in all textbooks, not just in some of them, all of them, right? So textbooks, introduction to condensed matter, going forward will have different equations, and they will include the term that Luttinger introduced. Luttinger called this the Berry connection J. Right? And he even took the curl of J, and he found that the velocity, the group velocity, is not just the gradients, right? It includes what today we call the anomalous velocity. I think this should be renamed the Luttinger velocity, right? Because anomalous velocity, what the heck's that? Right? But Luttinger fought for 10 years and then gave up, right? So the decade that he fought for this term is given by these two bookends. In 1964, because of this incredible resistance to his ideas, well, folks were very polite then, none of the bitterness that we encounter today. They would write in this very polite, hyperbolic language. Luttinger said, I cannot pretend to understand the opposition to these equations, but this is my last paper. And he quit the field. He quit working on transport theory. But lucky for us, he went on to make many more discoveries, right? Luttinger liquid, Luttinger volume, how to calculate thermal conductivity, which will be the subject of the second talk, and so on and so forth. But his contributions to these equations essentially ended in 1964. Adams and Blount were the two that couched this in this simpler term, which I will describe next. Anyway, here's the anomalous velocity. And as David pointed out in the nice review article by Chen Niu and his co-workers, they lay it all out. Okay, so what Luttinger found, as David already emphasized, that omega, if it exists, will have huge implications for the Hall effect, because this is a transverse velocity, right? Transverse well, there's no magnetic field, transverse to the Berry curvature. And he knew about the Hall effect. Oh, so one historical note, when Edwin Hall discovered the Hall effect in the late 1800s, he actually discovered the anomalous Hall effect because he was using nickel. And of course, the anomalous Hall effect is huge in nickel, and that's why he could see it. But then he went on and investigated other metals. So the very discovery of the Hall effect was, in fact, the anomalous Hall effect. And so Luttinger knew about that, and he also realized that omega will vanish if both TR invariance and inversion symmetry hold, right? So, and that is like 90% of the crystals that physicists would study. And so he proposed with couplers that this is the microscopic basis for the anomalous Hall effect. Now, to set the stage for the work of Blount, here's a list of names that kind of track this fight. So Luttinger recruited Walter Kohn as a young postdoc. I think he was a postdoc there. And they both basically set up transport theory long before Abrikosov, Gorkov, Jeloshinsky, and the heavy machinery that came with the Green's function. They basically laid down the foundations of transport theory before Kubo. And they worked out, and they kept getting this term, which I now switch to X for reasons that become apparent. Laura Roth, I think she was a postdoc with Walter Kohn, continued this work, but all this was gone when Luttinger stepped away from it. Blount, as I mentioned, couched it in this form that is much more physical. And there was a huge gap, right, from the mid-60s till around 82 with the Thouless paper, and then with Berry's paper in late 80s, 87. That the subject, it was realized what Luttinger was looking at. And Chen Niu, a student of Thouless, re-derived the semi-classical equations and basically recovered Luttinger's exact expression. Okay, so the way Blount and Adams looked at it is the following. In conventional block theory, we basically ignore the wave packet except when it's at the one-year site, right? So this is like Uber in Manhattan. You want to be picked up, but the Uber driver is using a very the first generation GPS, and he can only locate you if you're standing at a junction, right? That's what we're doing in block theory. And Blount pointed out that, well, what Luttinger found was this intracell coordinate, which I'll call big X, using his notation. So the position of the wave packet is the nearest Wannier site plus this little bit which points into the cell. Right? And this will turn out to be exactly the Berry connection. So when we teach solid-state physics, we basically ignore big X, right? This is tantamount to restricting our attention to the lowest band, the conduction band that the wave packet is in. And as mentioned and already explained by David, it's present in all crystals but vanishes by symmetry. And so had no consequence for all the technologically important materials, elements, and compounds. But as soon as you break time reversal, it becomes a huge force. And I'll show you an experiment where the Berry curvature expressed as an effective magnetic field is about 100 Tesla. Right? So imagine applying 100 Tesla to your crystal in the 50s and 60s, right? When you didn't have these pulse magnetic fields. Okay, so this just takes 3 lines. I put in a lot of details there. All right, so we have the usual non-interacting Hamiltonian in block representation. So the Wannier coordinate R appears as the argument of the potential, right? Whatever potential you're applying to. It's not the periodic. This could be, the electric field you apply or the impurity potential. Okay, so if you start by taking the commutator of X with itself, you find that it doesn't vanish, right? Unlike what the semi-classical theory assumes. In fact, what appears is the vectorial combination that gives you the curl of X, right? I think everyone's familiar with this. So this reminds you of the center of the cyclotron orbit in the quantum Hall effect. So the coordinates commute to a constant which represents an object that looks like a magnetic field, and hence if you calculate the velocity, right, by taking its commutation with h, you get this additional term, which at once gives you the Luttinger velocity. So 3-line derivation, and you see that it must be there unless omega vanishes. Now, I think Luttinger was well aware of this derivation, but he insisted on working it out from the start.
So, am I interpreting it correct that X is the Berry connection?
Yes.
Yes.
Yeah.
So
it's A, yeah. So
yeah.
fast forward 10 years and we'll call it A. 25 years. So I'm just using the historical notation because hopefully you will look up these papers and anyway, yeah, that's right.
Can you then follow up what, because it's this intracell vector, no? Because how can I understand?
Yeah. So if you now, define your position operator acting on some arbitrary function, and then you apply the completeness relationship of the periodic part of the wave function, then you see that the first term recovers big R, the Wannier coordinate, right? And the second term you will recognize right away is what we call the Berry connection. This derivation, unfortunately, is a bit heuristic because Blount recognized this. Well, this depends on convergence and degeneracy and so on. So there's a lot of hidden defects in this argument, but it gives you a feeling how this intracell coordinate becomes what we call today the Berry connection. Right? So as David explained, you switch your notation to A, and now it's a vector potential, but K dependent, not X dependent. And the curl, again, taking the derivative with respect to K, will give you the Berry curvature. Okay, so as I mentioned, Couples and Luttinger immediately proposed that this is in fact the explanation for the 50-year observation of the anomalous Hall effect. So a few words to remind you what the anomalous Hall effect is. Here's a good example. If you measure the observed rho xy, right, this is the Hall resistivity, versus field, it has an extremely rapid increase, and then it saturates. So that is the identification characteristic of the anomalous Hall effect. This slope is actually incompatible with the field you're applying, right? So this is less than half a Tesla, but it's increasing extremely rapidly. And this has been seen for 50 years. So here's the first test that Couples and Luttinger proposed. The current coming from this anomalous velocity does not depend on scattering time, right? As I forgot to emphasize that. Let me go back to that slide. So the Hall current comes from this term here, does not include tau, right? So it's dissipationless. And that was the problem. No one in the field would believe that you would have dissipationless current except in superconductivity. So if sigma xy does not depend on tau, tau of course appears in rho, right, the longitudinal resistivity. Therefore, the Hall resistivity should vary like rho squared, right? Because that's the only place that tau appears in. And at the same time, already mentioned by David, there was this competing skew scattering theory. I think this is identified with Berger. And Jan Smit, an experimentalist, fell in love with this picture, and he was right. Actually, half the experiments. Oh, okay. So what did they say? That the Hall conductivity actually is proportional to the scattering rate. So this is sometimes called the side jump theory. You imagine a wave packet hitting an impurity, and the quantum mechanics tells you that after scattering, it should step to the side and then continue. So this is called the side jump, and that gives you the Hall effect. So tau here in sigma xy should cancel one of the taus in the resistivity squared, and therefore it should be proportional to the resistivity. Right? Now, by modern standards, these tests are kind of hokey, right? A lot of things can go wrong. How do you know nature behaves this way, right? So most tests before the modern era were based on measurements in one sample. So how did they do it? They cooled the sample down from room temperature to liquid helium, 4 Kelvin, and they plotted the measured rho yx versus rho. That's it. That's the test. So it's sort of cheating because temperature is varying, the effective mass is changing, as Philip just emphasized, and scattering rates, they switch from different regimes. So the tests fell evenly on both camps, and this led to the dismissal of the Couples-Luttinger theory.
Excuse me, can I ask you something? Why didn't people try to separate the two with the frequency, right? So the intrinsic ones shouldn't be particularly sensitive to that, but the extrinsic ones will go away, because if you don't get to collide, you don't get to move, right? So
yeah, you will need to go to frequencies above the Drude edge.
Right.
So this is far infrared.
Right.
Yeah, and if you want to do Hall effects in the far infrared or infrared frequencies, that's a challenge, even today. even today? Well, these days you can do it in terahertz spectroscopy, but the sensitivity to the Hall angle is very low. Right? Nothing beats DC. All right, so now you fast forward. So we found in the early 2000s this series of materials actually was discovered by Bob Carver, my close collaborator. That's him. He found this amazing material, which is, when bromine is gone, when there's no bromine, it's an excellent metal with lots of carriers, right? And the direct exchange, the moments actually live on chromium. So think of this, chromium, the exchange between adjacent chromium atoms is what gives it ferromagnetism. The carriers are tunable, and they have nothing, they do not contribute to the exchange, right? Unlike in, let's say, nickel or iron, where the band, right, the conduction band gives rise to the exchange. So in this system, we were very fortunate that the magnetization doesn't really care how many carriers you have in there. Then we realized that this would provide a beautiful test of the Luttinger theory. So we persuaded Bob and his group to group a series of samples and measure the Hall resistivity versus temperature in every one of them. Right? And we found, to our amazement, that Luttinger is right. So when you plot rho xy versus the resistivity, you find a t-squared dependence. Well, it's pretty close. The exponent's 1.95. So this is what convinced us that the intrinsic mechanism is really there, right? So you imagine you have local moments that do not care about the conduction carriers, and they interact with the same direct exchange, give them ferromagnetism. Then you deplete the carrier density, and you just watch the Hall effect. So the Hall effect really doesn't, the Hall conductivity is truly dissipationless, as given by the square, the exponent 2. So this test, unlike the earlier generation of tests, was all done at 1 temperature. I think this is 4 Kelvin. And we vary the composition, the carrier density, rather than the temperature. So I made a mistake of showing this data to the group in Tokura's lab. They have this annual group meeting where they invite lots of people to their group meetings, and I talked about this, and this ignited tremendous interest in the Tokyo group, Tokyo community. All right, before I go to that, let me now switch to Berry phase and Berry curvature. So now we're fast forward to the late 80s, right? And Jen and David already showed this work here, which I'll go through very quickly. Now, this is Berry curvature due to spin texture in real space, right? Previously, the Luttinger theory was all in K space, and that involved this mapping from the Bray-1 zone torus to a sphere, which I'll show in a few slides. This is different. This is simply the good old precessing magnetic field that gives rise to the Berry curvature, Berry phase. So I'm sure you're all very familiar with the derivation. You solve the Schrodinger equation, but you allow the phase to be manifest. Then when you solve for the phase by doing an integration, you recover as the first term the conventional phase, the one that every wave function has. It causes it to oscillate in time. But you also recover this connection, right? And this has been seen many times, and most theorists dismissed it as, you can gauge it away, or it has no physical consequence. Berry made the important conclusion that if you took a closed loop, this never goes away. Right? In fact, it's independent of the path. It's always there, and in fact, it's the Berry phase. So we rewrite this term now as a connection, right? So it's A. This would be X before, and you see that the connection is the gradient, if you wish, of the state, and then multiplied by the state again. Okay, so this is all familiar. While we're on this, we can solve this exactly as Jen said. The eigenstates can be solved exactly if it's spin half, right? And they have this form. Once you know them, you can actually perform the calculation. So here's an example of, mathematicians have been trying to persuade us physicists to abandon vector notation. And, I can't do it. I'm too old. It's too deeply ingrained in my DNA. They said, look, you guys should not use vectorial language, switch to differential forms, right? But in the end, who cares, right? Just put it in Mathematica. But here's an example of how powerful this point of view is. If you express the Berry potential in a differential form, then it has this simple form, right? And if you now take it in this eigenstate, it's easy to take the derivative, as Jen mentioned, which will knock out this term and give you either 1 minus or 1 plus cosine theta. Okay. So to jog your memory, differential form is related to vector representation by this obvious thing. And now if you want to segue to vectorial notation, you have to divide by this awkward r sine theta, right? This length. Some mathematicians, authors of differential geometry books, will call the way we do it reliable nonsense. Because to them, it just has no mathematical rigor, right? But we use it, we love it. But anyway, we are stuck with this. Now think about this. If you want to calculate the Berry curvature in two form, as a two form, you simply take the exterior derivative, which immediately gives you this, right? However, if you want to do it the way that Jackson would do it, David Jackson would do it in his textbook, you would perform the curl, and the curl in spherical coordinates is 3 terms. All of them are non-zero, right? They all operate on this vector potential, and after a page of algebra, everything cancels, and you get the radial dependence. So this is what Jen showed before. So for the precessing spin half, you have a Berry curvature that's a monopole, and it has the usual 1 over r squared dependence. Okay, so how do we understand this? Very quickly, if the magnetic field, R, big R, circumscribes a cap, the area of the cap is given by this, 1 minus cosine theta. And then if you look at the Berry flux, which means multiplying the Berry curvature by the area, right? The Berry flux, this omega times S, it gives you 1 minus cosine theta times pi. And that's exactly the Berry phase, right? So for this problem, the flux piercing the cap is exactly the Berry curvature. So we'll come back to this simple interpretation in a while. All right, well, why am I going through all this? So as I mentioned, we had the original Couples-Luttinger theory, which is K space dependent. Nothing about, precessing magnetic field and so on. Then we have this real space representation of the Berry curvature. They both contribute in a solid. And they contribute when you have local moments that form a texture, right? So a very early example, there are others, where I'm showing stuff that my group did, was this colossal magnetoresistance material discovered by Tokura. Well, I guess not Tokura, by some guy at Bell Labs, sorry. But Tokura really took it and ran with it. That was his first major project. And we realized that this has an enormous Hall effect, especially above the transition temperature. So this is the Hall coefficient and also the resistivity as a solid line. So this is way too large for us to understand by using conventional theory. And we realized that it was basically the Aronoff bomb phase that comes from having canted spins, canted local moments. And we knew that Ted Holstein here, 30 years before, had thought about the hopping problem in a magnetic field. And he found that actually you can actually get a Hall effect that is proportional to the sign of the Aronoff bomb phase coming from the flux captured by this cone. Now, the argument is almost identical to the Berry curvature argument, right? But in experiments like these, many groups were already seeing phase-dependent Hall effects. Now, the killer experiment was done by the Tokyo group, Tokura and Nagaosa, on this. I think it's a spinel. Yeah. Anyway, yeah, these tetrahedron, and there are two kinds. One has moments tied to molybdenum, and the other is tied to neodymium. The molybdenum local moments have a very narrow solid angle, whereas the neodymium has one that's all split out, right? So the Berry phase, due to these, the spin texture will dominate depending on the temperature. And they could fit the Hall effect to this model, which was the first convincing experiment telling us that indeed the Berry curvature coming from spin texture could give rise to the Hall effect. But then, let me emphasize again, right? This is a spatially dependent Berry phase coming from spin texture. Yeah, I guess this is the actual measurement of the Hall signal interpreted in this way.
Sorry, one question.
Yeah.
Very naive question. In these atoms, in for example M shell or P shell, we have different electrons, and there are different directions of the magnetic quantum number, and they don't, by any chance, cancel each other out. How can one analyze that?
Okay, so yeah, I forgot to mention this. So the system is such that you have local moments, right? And let's first not discuss why they should be split. The carrier electron, again, the carriers are very few in number, and they act as spectators, right, that allow us to measure the Hall effect. But the electron, which is the carrier, will hop from one moment to the next. But when it sits on one moment, Hund's rule will lock its spin to the local moment spin. So you see as the electron hops around these three spins, its own spin will describe this solid angle that I mentioned before. Now, your question pertains to why should they be pointing up as versus down, right? Well, that's what your magnetic field does, right? It polarizes the texture so that you have more of this chirality pointing up than down. So here folks also use the term chirality for this situation where it's Si dotted into the cross product of Sj and Sk.
So what are you saying? There's kind of like a correspondence between having the winding number in real space of some moments and having topological bands in phase space? I mean, I guess...
No. These are separate things. So these are separate origins of the Berry phase induced Hall. Yeah, that's why I took pains to partition the two problems. Yeah. So magnetic systems themselves could have a band with finite Chern number, but that's like a dipping twice into the problem, right? Yeah. Other questions? Okay. Okay, so here's another situation completely different from before, where magnetic spin texture, now in the context of skyrmion physics, gives rise to a huge effective magnetic field. So this was discovered by accident in a collaboration between our group and my group and Tokura's group. We found that, okay, so this material, which belongs to some symmetry class called B20, these are the two primary examples. Fe germanium is actually the workhorse for skyrmion physics, but this came much later. So the first example was manganese silicide. They have very large Jeloshinsky-Moria exchange terms. And you can appreciate that if D is very large, it will tend to favor spin canting, right? Because it looks like, the chirality product that I talked about. In fact, the spin texture is so strongly favored that it forms a skyrmion. A skyrmion is one where the texture is spinned down, for example, in the center. Then as you move radially outwards, it rotates into up, right? So skyrmion is, of course, a field excitation introduced by Sturm in field theory. These materials, especially Fe germanium, form a skyrmion lattice. Now imagine an electron coming in and it scatters off one of these textures, right? As it does so, it's hopping between moments, and again, its spin is forced to rotate just like the underlying local moment texture. And therefore, you see a huge Hall effect. How large? Well, this gives you an example. If you are at zero field, let's say there's no Hall effect. Yeah, there shouldn't be any Hall effect. But then if you increase it to a fraction of a Tesla, you see this enormous increase. So we call this a mesa because it goes up and then it saturates. But then if the field is too strong, it dies, right? Because now the field is strong enough to destroy the skyrmions. So this, we felt, was caused by the skyrmion spin texture. And indeed, this is true. Now this has turned out to be the best way to look for skyrmions, right? You take any material and do the Hall effect. If it shows these mesa explosions of the Hall resistivity, then you know you have skyrmion physics, right? So this is like the touchstone for skyrmions. We estimated that, so let's see, I think it's the next slide. So here's a different way to plot it, this time as a conductivity. Oops, sorry. And again, conductivity has a huge contribution, and then it dies, right? And it's, as I mentioned, it's because the skyrmion, as it scatters the carrier, is forcing its spin to wind around before it lets the electron go. And it's an indication that the chirality is really dense, and that's what gives rise to this giant Hall effect. And these authors estimated that this enormous increase in the Hall conductivity is as if you have applied an effective field of 100 Tesla. So these are huge effects, right? They are.
I have a question. Why do you think that the momentum space very curvature cannot read the spin texture directly?
Come again?
What do you think about the fact that the momentum space very curvature cannot read directly the real space very curvature?
In a competition between the two. Thanks for bringing up that point. Actually, in this material, both exist. I didn't bring this slide. If you carry this to higher magnetic fields, you see that long after the skyrmion contribution is gone, you will see the classic anomalous Hall effect profile. So the band itself does have very curvature because it's a ferromagnet.
So then, why do they compete?
Well, they do compete, but the band contribution has it just can't compete against this enormous spike at low fields. All right, so if I forgot to bring it, I should have brought it. If you continue this to 10 Tesla, you see that this rises to a maximum and then it comes down, just like the anomalous Hall. So the two effects, the band Barry curvature and this skyrmion curvature, coexists, but one is so much stronger than the other. But it dies. It dies when you go to high fields. Was that your question?
Yeah, Because I always been wondering why the momentum space very curvature cannot read the spin texture directly. So
Cannot read. No, it is reading it. The manifestations occur at different fields.
that's the thing that I fundamentally don't understand. Why the momentum space very curvature and the real one cannot be just one by itself?
No, they come from different mechanisms. Yeah. Okay, one more large effect. Yeah.
What is the influence of pressure on your results?
Oh, this was, yeah, sorry, I forgot to explain that. So it turns out manganese silicide does not display skyrmions until you apply pressure. In this, I'm not sure you can see this. See this yellow region? So we think that skyrmions are only stable under pressure when you fall into this sector. Yeah, that's why the earlier workers who had studied manganese silicide never saw this. But once iron germanium was discovered, it appeared all over at ambient pressure. Yeah. Okay, the last effect before I talk about the quantized anomalous Hall effect is the planar Hall effect. So this is a semi-metal. It used to be thought that this was also displaying the chiral anomaly, but we don't believe that that's the case anymore. It wasn't claimed by us, by another group, but we also, this is a very well-studied Dirac semi-metal. The reason is, so by RPES, you can actually see the Dirac cone very clearly, right? So it tapers to a point, but with mother's eyes, you sort of realize that the top has been chopped off, right? So it's actually a very tiny Dirac hole pocket sitting under a significant gap, and therefore it's a Dirac system that allows a gap to form in the node, right? So it's not quite a Dirac metal. If it had been a protected node, when you apply a magnetic field, it should separate out into two wild nodes, as Jan explained, and then you would see the chiral anomaly, right? So we think that the negative longitudinal magnetoresistance in this material is coming from a purely classical distortion of the current density. There's a whole review paper that we wrote to explain that. But anyway, it has something much more interesting, I think. When you measure the Hall effect, you see all kinds of crazy patterns. And let me just single out one of them. So this is the raw data, right? Focus your eye on the blue curve, right? It comes down, has a minimum, then it swings positive, has a maximum, and it comes down. So these high field branches are parallel, right? So that tells you that it's the combination of the ordinary Hall effects, which is very large because the carrier density is so low, competing with the Berry curvature Hall effect because you're applying a magnetic field. And what my student did was to subtract off the uninteresting conventional Hall effect, and what remains then is this classical anomalous Hall effect field profile. So this thing is chock full of Berry curvature, and it's not surprising, as I'll explain in a minute, that if you have a Dirac node sitting there, the Berry curvature in K space is very large. It won't be exactly as large as a Dirac node that's protected, but it's perturbed away from that. Right? So there's a huge Berry curvature monopole sitting there in K space, and that we think is betraying its presence by this anomalous Hall effect. Now, what's crazy is that if you now tilt the magnetic field into the plane, I've just expanded this figure here. So the magnetic field that you apply lies in the plane of the Hall contacts and the current, right? So Lorentz force should be absent, right? But the magnetic field generates a Berry curvature that has a huge component along the z-axis. And this gives rise to this signal. When you reverse the magnetic field, still planar, it also reverses sign and gives you a negative Hall signal. This, I believe, is the first example where you have a planar geometry, right, field in the plane, but you get a Onsager response. Onsager meaning that if you reverse your magnetic field or you reverse your current, the Hall also reverses. Right? Now, there is a 50-year history of the planar Hall effect that applied physicists have been working on. If you take thin films, you put the field in the plane and you rotate it, you will see what they call a Hall, a planar Hall signal. That is bogus. Right? That's basically angular magnetoresistance. So I'm on a one-man crusade to convince this huge community that they should drop the word planar Hall effect, because Berry curvature physics gives you a true Onsager planar Hall effect. Not very successful, but the experiment is there. Okay, so this sets the stage for my thermal Hall talk on tomorrow. Yes.
Can I ask you something? So when you say that magnetic field generates Berry curvature, do you mean that it lifts degeneracy between plus and minus Berry curvature of the two degenerate bands?
No, not necessarily. We don't know the actual mechanism, but theorists tell me that, if they write down the free energy, right, the applied magnetic field tends to couple to the Berry curvature. So the coupling.
Magnetic field, the two bands are degenerate, and they have opposite Berry curvatures. So, of course, you don't get the Hall effect. Once you apply magnetic field, you polarize them. There is more, one spin compared to the other. And you get
no, it's not the Zeeman field. It's too big, and also it's in this crazy orthogonal direction. You will see this in the ruthenium chloride in the talk tomorrow. Yeah, maybe we should discuss this further. 5 minutes.
So it's safe to say that
I only have 5 minutes.
it's safe to say that the origin is not fully understood, right?
Yeah. I think that's
There's
right.
only a non-abelian very case.
You think it's not?
Yeah, but that's a small thing. Right?
Yeah, I would love it if you would work on it.
And actually, we recall on this. Is it obvious that the magnetic moment, like the orbital?
No, this is totally non-magnetic.
No, the orbital magnetic moment.
Orbital magnetic moment.
Yeah. Is it obvious that it doesn't give a
It could, yeah. Lots of people have reported the band structure calculation.
But you need a gradient to that to your current because it contributes to whole. I mean, maybe I don't understand what you mean, but the curls of magnetization is current, so cannot be the whole thing.
Yeah, but like.
Okay, let's resume. All right, so the final dramatic appearance of the Berry curvature is in this famous work of the discovery of the quantum anomalous Hall effect. So let me just quickly step you through the argument. So all of you remember graphene, so it has a Wannier 2 spinner, right? A sites and B sites. And if you solve for the diagonalized in the block representation, chi being defined by this Mercedes-Benz threefold phase, and then you find that you get Dirac nodes, right, with a zero mass, and then you can treat D, the vector D in this situation has the components x and y, perhaps m if there's a gap, as a magnetic field, right? So it's an effective field that polarizes the Pauli spin matrix. And then you can just pull over the data, the results we got that Jen reported on which predicts that there's a Berry curvature now at the Dirac node. But this time, it's a Berry curvature that is in K space, right? Not in real space. Okay, I don't think I need to repeat that. So many people had realized, I first learned it from reading the work of Suchen Zhang's group, that you can actually map this Hamiltonian, which lives on the torus, right? Torus because in 2D, the Phuan zone repeats in both directions. At every point on the torus, there's a patch here which disappeared. Yeah, you can barely see it. There is a wave vector, and if you scan this patch, the wave vector which maps onto the unit sphere will also raster scan some patch, right? Now, as you let K roam over the entire Brillouin zone, this patch may grow, and if it covers the whole sphere, you have Chern number of 1. Okay, that's the secret to this mapping. But in most materials where the Chern number is 0, the patch will grow, then barely reach the equator, and then magically it will shrink and erase itself. So that's a trivial, topologically trivial system. Okay, that's all I want to say. This basically repeats it. So in the last few minutes, let me quickly walk you through the Fowler's derivation, because this is such a central result for quantum transport that I think every student should know it by heart. So you start off with the non-interacting band that I wrote down before, and you put in the perturbation, which is now your electric field. Right, and you use Warnier coordinates. The Warnier coordinate in K representation is the derivative of K. Now we specialize to the case where the electric field is parallel to X, and then just do first order perturbation theory. And all of you know how to do that. So the perturbed wave function is the unperturbed one minus this correction that is proportional to H1 or E. So you have this, what appears to be, right, the beginnings of the Berry connection. Now we want to calculate the expectation value of the transverse velocity, Vy. Right? Remember, E is along X, and we are interested in the velocity along Y. So take its matrix element of this equation, and now you have this matrix element appearing in the summand, and this is the key step. So if you treat the velocity as a commutator of the unperturbed Hamiltonian, you find that the matrix element here can be expressed back as a connection, right? You're going to see that the connection appears here and here, right? And the difference of the energies cancel out, and you get this very simple expression for the expectation value of the velocity. Okay, so finishing it up, then the Hall conductivity is the velocity here multiplied by the number of carriers in the band, and you find that the summand has this very tantalizing form, which if you again define the connection as we did before, this is exactly the curl of A, now written as in vectorial notation. So this was derived by Fowler's TTKN, Komoto TKNN, and had no impact on the problem of quantum Hall effects. But it was much more important as topological, as opening the door for topological physics. And so everything reduces then to the integral of the Z component of the Berry curvature, which is defined to be the Chern number. And it turns out that this definition exactly recovers this wrapping winding number argument that I had before. Okay, so finally, let me talk about, so I should introduce the topological insulators, probably unnecessary. So very quickly, this was discovered by Fu and Kane, and then a little bit later by the Stanford group as well. So you have a insulating bulk, right? But if the surface states have band inversion, they will have Dirac nodes at the crossings. Furthermore, if the crossings occur at what these folks call time reversal invariant momenta, which is just a fancy way of saying they occur either in the zone center or at the corners. Then the direct node is protected. Nothing you do to the topological insulator will kill that node, and thus basically constitutes a topological insulator. Then our theorists were telling all experimental groups, add ferromagnetism to it, and you should see quantized anomalous Hall effect. So needless to say, everyone tried, but the group in IOP and Tsinghua, led by Chikun Shui, pulled it off. And this is a very challenging task because once you put in chromium, I think they used, I didn't write it down. They dope it with chromium in the bulk. You completely wreck the system. So my collaborator Kava did this, and it was just completely it destroyed everything. But they used MBE, which Chikun Shui was a master at, and they grew the best films. The mobility sucks. Even in these devices, the mobility is only 20 centimeters squared per volt second. Right. Nonetheless, despite this very low mobility, their very first samples already showed this incredible step. And my former student who did the measurement for them said that they just couldn't believe it. Right? At 30 millikelvin, they'll be happily going here, and then boom, it goes, and it's just dead on. Reaches 1 in universal constants, plus or minus a few percent. More importantly, the resistivity is only large at finite field, and it basically vanishes at high fields. So this has been repeated by many groups. Within a year, remember there were like 10 groups chasing after this problem, maybe more. Within a year, many groups reproduced it. Here I'm showing some of our results on samples grown by Nitin Samat at Penn State. And here we think this is the record. It's as close to 1 in terms of almost 10 parts per million. Competing with graphene, certainly not as good as gallium arsenide, but not bad for such a dirty material. One thing we found was that the resistivity in between actually drops to almost dissipationless. It's very low. But the most interesting thing, I think, is when you change the magnetic field to the wrong side, you induce transitions from the wrong churn state to the correct one, right? But it doesn't happen smoothly. It happens as random jumps. And we think this is caused by supercooling in a magnetic field. But anyway, so this is my last slide, and I thank you for your attention.